everyone, today I will be presenting a framework to reduce latency in machine learning pipelines that are typically deployed in factories. So first I'll give an introduction about computer vision and talk about the challenges of deploying computer vision pipelines into a factory setting, and I'll talk about the framework that I'm proposing to overcome those challenges. We'll go through an example of this framework, and finally I'll finish up with some conclusions. I am a machine learning engineer working for MEQProbe. We are an Australian startup that works in the agricultural technology space. But before that, I used to work for Nasdaq and Google in multiple technical roles. Let's get started with a quick introduction to computer vision. So I specialize in computer vision, which is the field of computer science that focuses on building systems to extract information out of data. And the way we do that is in a very similar way to what humans do it, by looking at patterns. So in short, machines interpret images as a series of pixels, each with their own set of color values. So for example, we are looking at a picture of a very blurry Abraham Lincoln, where each pixel's brightness in this image is represented by a single 8-bit number. So it goes from 0, which is black, to 255, which is white. This data is then provided as the input to our computer vision algorithm that will be responsible for further analysis and decision making. Some of the common challenges that we face when we deploy systems into a factory some of them are very similar to what any data engineer faces when deploying systems into any type of environment. But on top of that, on top of the data and accuracy challenges, we also have space limitations, and we are, of course, not always able to mount the systems that we would like to. We also have usually poor bandwidth and reliable connectivity, and sometimes no internet at all. We have to ensure that our systems are product safe, that they are waterproof, that they are dust proof, they are complying with the hygiene regulations. And finally, we also have to make sure that the predictions happen at the speed of the chain, otherwise they are pretty useless. So this is an example of a typical machine learning system that we would be building. In this case, we're talking about an object detection system that needs to classify and detect different types of food that go through a conveyor belt. And this has to be without relying on internet, and there has to be a prediction going back to the operator. So this is an example of how our system would look like. We have different types of product coming through the conveyor belt, and then we have our computer vision algorithm displaying the results and the confidence score back to the user interface. The challenge that I face with this is that there are not many frameworks for designing pipelines that comply with those requirements. So I did some research, and today I'd like to share the results from that investigation and propose a method for selecting different components and layers of this pipeline. So this is the framework proposed by the researchers from Cornell University in England. So they suggest that in manufacturing industries and in processing plants, there are 4 key data layers that every pipeline should have, and these are data source, raw data transmission, data communication, processing and analysis, and finally data visualization. But what I find is that, at least for our case, the 3rd layer has too many responsibilities, so I am proposing that it's better to decouple them and to also specifically add machine learning components to the process. So what I'm proposing is to have a separate machine learning service that contains a processing and a model inference data. So as an example of this, we can see that the graph explains the proposed design and the project constraints. So we're going to be building an end-to-end pipeline for object detection that is going to be streaming high-definition images. So the different components are shown in yellow in the right-hand side. So as we can see, the high-definition images from the connected cameras are uploaded or streamed to a local storage, which triggers the sending of the image metadata to a message broker. On top of that, a machine learning service pulls the works items from the queue and runs a prediction on those images. The prediction then gets shown in a user interface. As we can see, this visual inspection is a time-constrained process, and the time components are shown in gray. So the main challenge of this pipeline is to ensure that the prediction time for that object is less than the elapsed time before the next food item arrives in the conveyor belt. So in our case, this is generally around 1 or 1.5 seconds. Let's start with layer number 1, data source. And in this case, we define a data source in terms of its root source. So under our definition, a database is not a data source, but a data lake. In general, there are 4 main types of data source used in factories or in processing plants. Sensors are by far the most ubiquitous of all big data sources in the manufacturing industry. And this is not surprising because there are many different types and functions and uses for sensors. But also cameras have been used to capture images of products and on the production line. And then RFID and barcodes are basically printed labels that store information about an item, which is usually a product, to track its location and state. And then 5%, I would say, of all the data sources are machine PLCs that are designed to receive signals from input devices such as sensors, and then use the inputs to control output devices such as switches. They can be considered mini computers that store data. Cool. So in our case, of course, we're going to be going with the cameras because we're building an object detection system. Layer number 2 is raw data transmission. So we define raw data transmission enablers as the technology that allows us to move the data from the source to the point in the pipeline where it's first exploited. So examples include IoT enabling microcontrollers, but also communication protocol software and hardware technologies that are used for harmonizing data that comes from different sources. And as well, we see some situations where some engineers decide to use removable storage devices for transferring data from a PLC or microcontroller to a computer that hosts big data software tools. We decide to go with wired connections to stream the data from the cameras to our NUC device. And it's important to note that the decisions that you make regarding the type of data transmission enabler that you're going to use are going to really affect the time that it takes for your pipeline to run. So for example, we decided to go for a 10 gigabit per second switch. So we are able to stream those images, maybe like 8 high definition images in less than 6 milliseconds. But if we would have gone for something like a cloud upload, that would probably take much longer. So we're talking about half of a second, maybe, the time that it would take to be uploaded into S3 bucket or something like that. So it's very important to know that the decisions in this step are going to really affect the time that your data pipeline takes to run. So in some cases, ingestion and communication tasks are handled by the same tool, but I think, I'm not saying this is ideal, but I think in general, what the industry prefers is a publish and subscribe communication model that has message compression. And we agree that this tool should be capable of both real-time and bulk data transfer. This is probably the best part of the conference, which is when we talk about machine learning. So as a machine learning engineer, I get very excited when I train a model, and I'm very happy with it. But then when it comes to deploying that model into the system, this is usually when I struggle with the data engineer, or I have some trouble. Sometimes the model that I deploy does not generate the same results as the trained one, or does not align with the system's requirements. So I'm going to go through some techniques that I found useful to overcome those challenges. And by the way, I like using TensorFlow, but I know that there are other technologies available for creating machine learning services as well. That should be good as well. This is probably the most common phrase used in machine learning, but it's good to start from the basics. Garbage in, garbage out. So this means that the quality of your model, your results are highly correlated to the quality of data that you receive. So I'm saying this because I think that having this in mind, we are able to also build better machine learning components and add some mechanisms to ensure that the data that we are receiving in real time in our deployed model has also maximum quality and is aligned with what we were expecting. And this is when data validation comes to play, because if we introduce data validation, we would be able to catch errors like blurry or noisy images, to spot if the image is in a wrong size, to see if the image is corrupted, to maybe alert if the cameras have been moved and now we are recording a different conveyor belt than the one that we were recording originally, or even if the data distribution has completely changed. So maybe we're seeing a lot of classes. A particular class has been increased in the data distribution. So this is also going to be a challenge for our machine learning model. But if we include data validation, we're going to be able to catch these errors and potentially even correct for them. So we can use image transformations like resizing, cropping, rescaling, adding a white balance, adding some color correction, including padding. And in this way, we're going to be able to ensure that the data that is fed into the model is high quality and is what we were expecting. But these transformations can be applied individually within a dataset object, which means that is we apply these transformations as a series of steps to a bunch of images, or also within the model, which means that we add a custom layer that applies all transformation as after the input layer, but before the machine learning calculations are actually done. So TensorFlow offers different options to be able to pre-process and convert these images into a machine learning format. Now I've done an experiment with 3 of these methods, and I think that the results are pretty self-explanatory. So we can see that there's a huge difference between some of them that are even like 6 times more efficient. And in my experience, the rule is usually that the hardest it is to code, the most efficient is going to be. For example, the 2 bottom methods require only 2 lines of coding, but creating a TF.data set is probably around 25 to 30 lines of code, and it allows a lot more customization. For example, typically what happens when you're running transformation is that the accelerators sit idle while the CPU is applying the transformations to the image. But what you can do is you can include a prefetch option, and this would actually make your TF.dataset object run much faster as well. And then another question that I get asked quite often is if it's better to batch the data in a bunch of images, or if it's better to make predictions, to make an inference on every image at a time. So I think, of course, it really depends on the requirements of the project, but in my case, I find that large batch sizes need more memory to store tensors, and I think everyone agrees with that, but they reduce the amount of communication needed between different operations. So overall, it reduces inference time to batch images. But there's a certain point at around a certain batch size when the runtime stops decreasing. So in my case, for this particular project, that number is 8, a batch size of 8, but really depends on the hardware that you're using. Finally, we're going to talk about model inference. So we look at 2 main performance metrics when we are thinking about the components for this layer, and those are inference time and other accuracy metrics. So inference time does not include the time that it takes for us to load the image, to decode the image, or to transform the image. It's the time that it takes for the algorithm to return a prediction. And remember that in object detection, we are trying to localize the object, but also to classify the object into the correct class. So in order to account for those two metrics, we look at MAP and IOU. So these are the most typical object detection metrics that we use to try to understand how accurate our results are. So IOU measures how much does a predicted box overlap with the true box, and mean average precision measures the area under the precision we call curve. So there's also something important to understand when we're using object detections, and this is why I think these are such important metrics that we need to consider when we are choosing the components for this service, is that different object detection algorithms have, of course, with different precisions, but at the same time, some of them take a lot longer to run a prediction. And this has to do with the way and the different methods the architectures are built. But that would be a completely new talk if we go deep into that. I just want to highlight that, there's always a big trade-off between a more accurate model and a faster inference time. So in this case, we can see that the fastest and the best model is YOLO. In this case, I'm using YOLO v4, but I'm also running YOLO using TensorRT to make it even faster than if it was running just using darknet. And finally, moving on to our conclusion, we can say that the latency in the system pipeline is dominated by the model inference time and the data upload/data streaming. So these two components, the decisions that you make in those two components are going to play a huge impact in the time that it takes for the model for the whole pipeline to run. And specifically in object detections model, there's a clear trade-off between speed and accuracy, but we can also improve inference time by removing certain layers in the model, reducing the input size, or even doing changes to that model's architecture. And the data upload time can be reduced by compressing the images if you don't need to have such a high definition image, by running concurrent requests, by using maybe wire connections or a higher bandwidth. And I think that overall, what I want to say is I feel that there's a need for more machine learning specific data engineering pipelines, and hopefully we will address that challenge soon. Thank you very much.